Ever get that feeling like you're just scratching the surface? I mean, you look up at the night sky and see this vast universe with its stars and galaxies and planets all moving around in their own little orbit, and it hits you. This is all happening in 3 dimensions. Three. And for some reason, our brains kind of go, hold on a second. Is that it? Is there more to this story?
Yeah, I get that. It's a question that has haunted physicists, like for ages. Why three spatial dimensions? We experience it so viscerally, yet there's this nagging thought that reality might have a few more tricks up its sleeve.
Exactly. And today we're tackling a theory that suggests those extra dimensions might be more than just science fiction.
Yeah, and we're going beyond string theory here. The article we're diving into, could extra dimensions solve the biggest mysteries in physics? It presents a totally different approach to this whole extra dimension thing. And get this, it might actually explain some of the biggest puzzles in cosmology.
Okay, so let's start with the basics. 3 dimensions, up and down, left and right, forward and back. It's so fundamental to how we experience the world. But then you think, why three? It's got to be more complicated than that, right?
Right. It's so ingrained in our experience that we rarely even question it. But the idea of extra dimensions, it's been around for a while. Early 20th century, actually. The real head scratcher has always been, if these extra dimensions are out there, why aren't we bumping into them?
Right, exactly. They should be, like, obvious, should they? So where are they hiding?
Well, that brings us to this wild concept called compactifications. It's all about scale.
Compactification, huh? Sounds a bit like tidying up the cosmos. So how do we wrap our heads around these hidden dimensions? Give us a visual.
Imagine a thread, really thin, from afar it looks one-dimensional. You can only slide along slink, but zoom in really close and you'll see it's got a circumference, like a tiny circle. That circle, that's a second dimension, but it's so small, it's effectively hidden unless you look close enough. Now, the idea is extra spatial dimensions could be doing something similar.
They're like curled up so tight we just can't see them. It's like the universe is hiding its secret compartments, right?
Right, compactified, hidden from our everyday experience. But here's where things get interesting, because even though we can't see these tiny dimensions, they could have huge implications for the physics of our universe.
Okay, so these curled up dimensions, they're not just sitting there looking pretty, they're actually affecting things. How does that work?
Well, it has to do with the fact that at a fundamental level, particles are kind of fuzzy. Not like little billiard balls, but more like waves. That's the whole wave-particle duality thing. Still blows my mind sometimes.
Yeah, I mean, it's hard to picture, but I think I'm getting it. Particles are kind of doing the wave.
Exactly. Now, if a particle's wave is trapped in one of these tiny compactified dimensions, it can only vibrate in specific ways. Think of a guitar string. You can pluck it to get the fundamental tone, but you can also get those higher-pitched harmonics.
Right, right. Different notes from the same string, but it's all about how it vibrates. Okay.
Exactly. And each of those vibrations, those harmonics on the guitar string, represents a different energy state. So this theory says that each of these different vibrational patterns within the extra dimension, they correspond to a different energy level of the particle.
Okay, so instead of just one particle, there could be like a whole bunch of them, each heavier than the last, because they're vibrating differently in these hidden dimensions.
That's the idea. What we see of a single particle could be just the tip of the iceberg. A whole tower of particles, each a heavier version of the original, all because of these hidden dimensions.
A tower of particles, that's pretty wild. So now we have these hidden dimensions and these like secret families of particles. How does that connect to the Big Bang and how the universe evolved?
This is where the theory gets really exciting. They propose that this tower of particles could have driven a specific phase in the early universe called cosmological stasis.
Cosmological stasis. It sounds like the universe took a chill pill before things got really wild.
Uh-huh, yeah, kind of. The idea is that just after the Big Bang, tons of energy would have been distributed across all the levels of this particle tower. And then, as the particles in those high energy levels decayed, it created a kind of pressure, like steam building up in a pressure cooker.
Okay, I'm with you. So this pressure would have pushed the universe outwards, making it expand. But how is that different from the regular expansion we know about?
Well, during the stasis period, the universe was expanding, but it wasn't doing other things we normally expect, like matter wasn't clumping together to form stars and galaxies right away.
It's like expanding, but not really changing, right? Just stretching out the fabric of space. So what flipped the switch and ended this era of cosmic chill?
Here's the elegant part. The stasis naturally ends once all that initial energy in the particle tower is used up. Once those high energy levels are empty, the pressure drops, and the universe can transition to a more familiar expansion phase.
So it's like a self-regulating mechanism, starts and stops the rapid expansion all on its own. That's pretty neat. It's like the universe had a built-in timer. But then what happens to all those extra particles in the tower? Do they just disappear?
This is where it gets even more mind-blowing. The theory suggests those leftover particles, they could actually be what we call dark matter.
Dark matter. Okay, so we've heard a lot about dark matter, this mysterious stuff that makes up most of the universe's mass. But what makes these leftover particles good candidates for dark matter?
Well, for starters, they're heavy, and they don't interact much with regular matter, which fits the description of dark matter perfectly, but there's more. This model specifically suggests these particles would be what we call warm dark matter.
Warm dark matter. Now, I've heard of cold dark matter, but warm. What's the difference? Do they wear wetters?
Haha, not quite. It's about how fast they're lipping around. Cold dark matter, the more traditional idea, is slow and clumpy. It likes to form dense halos around galaxies. Warm dark matter, it's better and faster, so it's less likely to clump on small scales.
Ah, so it would move things out a bit. And that could help explain some of the things we see in the universe, like how galaxies are distributed, right?
Precisely. Some of the discrepancies between cold dark matter predictions and actual observations, they might be resolved if dark matter is actually warm. And that's one of the things that makes this theory so exciting. It's not just abstract math. It connects to real, observable stuff.
That's what I love about physics. When a crazy theory suddenly clicks with something we actually see out there in the universe.
Okay, so we have this theory. It's elegant, it's thought-provoking. But how do we know if it's actually true?
That's the million-dollar question. The good news is this theory makes some testable predictions. We could potentially see evidence of this cosmological stasis phase in the universe today. Testable predictions. That's what separates a cool idea from actual science. So what kind of evidence are we talking about? What should we be looking for?
The article talks about a couple of possibilities. One is gravitational waves. The transition out of stasis, that sudden shift in the universe's expansion, it could have created ripples in space-time, gravitational waves.
We'd be talking about like echoes from the very beginning of the universe, right? That's incredible. But how could we even detect something like that?
Future gravitational wave observatories, they might be sensitive enough to pick up these unique patterns if they exist. We're talking about some serious next-level astronomy here.
Wow, just wow. Okay, so gravitational wave. What's the other potential smoking gun?
The cosmic microwave background, the CMB, it's the afterglow of the Big Bang, the oldest light in the universe. This stasis phase, the way it ended, it might have left a subtle fingerprint on the temperature fluctuations of the CMB.
Like a cosmic watermark from the earliest moments of the universe. So we're talking about looking for tiny variations in this ancient light.
Exactly. And some scientists have already noticed some weird correlations in the CMB data that this theory might explain.
It's like putting together a giant cosmic jigsaw puzzle, looking for those pieces that fit just right. Now, despite all this, the article does use the term mathematical fiction when describing this theory. What does that mean? Are we just dealing with a fancy story here?
It's important to remember that theoretical physics often deals with ideas that are, well, theoretical. We build models, we explore possibilities using math, but that doesn't automatically mean they perfectly reflect reality. Mathematical fiction is a way of acknowledging that we're dealing with ideas that need further exploration and confirmation.
So it's like a stepping stone. It might not be the complete picture, but it could lead us in the right direction.
Absolutely. And even if a specific theory doesn't hold up perfectly in the end, the process of exploring these unconventional ideas, it often leads to new insights and discoveries down the line. That's how science progresses, right? We build on the ideas of those who came before us.
So to sum it all up, today we dove deep into the fascinating idea that our universe might have more dimensions than we can see. This theory suggests these extra dimensions could have played a huge role in the early universe, driving a phase called cosmological stasis, potentially giving rise to warm dark matter and leaving behind clues we might be able to detect today.
Yeah, it's a reminder that even something as basic as the number of dimensions, something we think we understand, could be far more complex than we realized.
And it really makes you wonder, if there are extra dimensions out there, what other fundamental things about the universe might we be missing? What other surprises are waiting to be uncovered? It's questions like these that keep us exploring, keep us pushing the boundaries of what we know. Thanks for joining us on this deep dive. Until next time, keep those minds open and those questions coming.